Hello everyone, welcome back to the channel. In this video lecture we shall solve this problem subset sum problem. So in this problem we're given a set of non-negative integers, that means integers which are positive and there can be 0 in them, and we are given an integer sum. We have to find if there is a subset of the given set which has sum equal to the given sum. Okay, so that's what we want to find in this problem, right? So the input format will be given a set of integers or an array of integers, n integers, and an integer sum which represents the target sum, and in the output we have to return true or false, okay, depending upon the existence of the subset which sums up to the target sum. Okay, so if there exists a subset which has a sum equal to the target sum, then we return true, otherwise we return false. And for instance, in this example we have 3 4 5 2. This is the input array and the target sum that we require is 9. The subset which has sum equal to 9 is 4 5, hence the answer is true because there exists a subset which sums up to 9. The constraints of the problems are: the length of the array goes up to 100, that means the largest array that we can have is of length 100. Okay, it doesn't exceed 100. While the numbers inside the set, inside the array, they also goes up to 100, while the sum, the target sum, may go up to 10 raised to the power 5. Okay, so let's better understand the problem with example. So this is the example that we are given, and the subsets that we can generate are these. These are the possible subsets that we have. First we take subsets of size 1, and out of all these subsets, none of them sums up to 9. Then we take subsets of size 2, so this gives me 7, the sum is 7. Sum of this subset is 8, okay, not 7, it's 8. The sum of this subset is 5, okay, the sum of this subset is 9. Yes, this subset, so this subset is basically giving me the target sum, hence the answer for this is true. Okay, so what is the approach that we are using to solve this problem? Here I'm basically building all the subsets and checking if the sum of each subset equals this sum or not. So if even if a single subset has sum equal to this target sum, then the answer would be true. Okay, so let's see what how we can generate all the subsets. To generate all the subsets, we have an algorithm which runs in big of 2 raised to the power n time complexity. In this algorithm, what we do is basically we try to generate all the subsets starting from the first integer, and there are two options: either take that integer or do not take that integer into the current subset, and so on. Fine, so let's just think of the solution here. Okay, so imagine, okay, so this is a test case. Let's try to build a naive or brute force solution for this problem. Okay, so we have this target sum and we have this array. We want to build this target sum from the set of integers which are given here. Now initially, let's say we are standing at this location. We start from the last integer, so we have 4 integers and the sum that we require is 9. Okay, so let's say this is the final subset which we have, which sums up to 9. Okay, so this is imagine this subset. Now here it is empty and we are standing at this integer. Now there are two cases for this integer. Maybe this integer is present in the subset or it is not present in case it is present in the subset, then all we have to do is to find the integers, pick integers from this part of the array, okay, which sums up to 7 or 9 minus 2, because 2 has already been included in the set. So we have 2 now. The remaining integers are these 3, 4, 5. Now what I'm saying that, okay, take sum of the integers from these integers, which sums up to 7. Fine. So that's what I'm saying. Another way is that I do not take this integer. So what I'm saying, okay, maybe this is not present in the final set. In that case, the sum that I am trying to build will be built using these 3 integers, and hence I will use the first 3 integers to build the solution, and the target sum stays the same because we are not using this integer to build the final set. Okay, now again here I have set which contains 2, and now I'm standing at integer number 3, and again I have 2 options because the target sum that now I want to generate is 7 here. Okay, so the target sum is 7 while here it is 9. Okay, now the question is, can I include 5 in the generation of the final subset? And the answer is yes, because 7 is greater than equals to 5, and 5 may contribute in the final set to the final sum. So let's take 5 as well. It would give me 7 minus 5. Now I have taken in this set 2, and okay, and here I'm not here the second option, which is just skip this integer. So if I skip this integer, then I would have this state like this. Okay, and the set that here would be present contains only 2. Okay, and so on. Again, now I am standing at second integer. Now I ask, can I include this integer in the generation of the sum 2? And the answer is no, because I want to generate 2 while the integer is 4. So 4 is greater than 2, hence it cannot be used to generate 2. Therefore this option, that means using this integer, is not allowed. Rather, we simply skip here. So there is only one option remaining in this case, that is just move to the previous integer and keep the sum as it is. The set is 2, 5. Fine, there is only one option for this case, while here I have 2 options because I'm standing at second integer and I'm asking, can I use 7, can I use this 4 to build this? And the answer is yes, I can use it. So I use 4, and the function call, the next state would be this 7 minus 4, that is 3. Now here what I am doing, I'm asking, okay, the target sum that I want to generate is 7. Okay, I want to generate 7 and check if 4 can be used for generating 7, and the answer is yes, it can be used because 4 is less than 7. So here I am using 4, and therefore I subtracted 4 from this 7. Now here the set that I would have is this. The set I have here is 2 and 4. Okay, because here I used 2 and here I used 4. Okay, so this is not. Then I am standing at first integer, which is this. Now I ask, can I use this integer to generate my target sum 3? Yes, because 3 is equal to 3. 3 is equal to 3. They are same. Definitely I can use it. Hence, one of the options is just use this, and the target sum becomes 0, while the set becomes 2, 4, and 3. Here you see that the set has become 0, and like the sum has become 0. Now I want to generate 0 sum from 0 elements, and that is true. It can always be generated. Hence the final set is this, which says, okay, use integer 2, 4 and 3 if you want to generate 9. So this is the branch. Let me point out. So this branch, this branch is giving me a favorable output set. So this branch is giving me a favorable output set, that is 2, 4, 3. So since I have got this, I will return true from here, true, then this will return true here, this will return true here, and this will return true further here. So that's how the true will be propagated up until the root of the tree. Okay, but there's a question that maybe this function call here may return false. So to handle that, what I would do, I would just OR this true with the false. So no matter whether this returns false or true, even if one of the functions, even if one of the branch leads to the favorable set, the true will always be propagated to the root of the tree. Okay, so I hope you got the idea where we are going. Let's see this in a more programming language view. So imagine a function is subset sum. Okay, so this function basically tells me whether this sum can be generated from the n integers that we are given. That's what this subset sum function is asking me. Okay, so it returns true if it is possible, otherwise it returns if it is not possible. Fine. So let's call it a function ISS. Initially the function is called at fourth integer or nth integer in a generic case for the sum 9. Okay, so we are just trying to build the body of this function, how the body of this function will look like. You can see that I'm standing at last integer. I would have two options, either include this integer in the building of the final set or do not include this. If I include this, then I have to subtract that integer from the target sum. That would give me 7 because 9 minus 2 is 7. And second case is just do not take it and skip it. It would give me 3 because I am moving one step to the left, and the target sum stays the same, and so on. Here two options here, two options here, and so on. Finally at the bottom I would have some sets prepared, some set here, some set here. Okay, one of the sets would be 3, 4, 2. Okay, and so on. So this set, okay, this set would basically gives me this target sum, and hence from this function call I would return true. Okay, so this will return true here. So maybe this function call is returning false, but since I want my true to propagate up to the root of the tree, because I know I have found at least one subset which sums up to this target sum, hence I want to return a positive answer to the calling function. So for that I will use a OR operator. Okay, because false when ORed with true, it always gives me fine. So if we do this, even if we have a single subset which gives me the target sum this, it will always be propagated to the root of the tree. So that's the idea. That's how we build the body of this function. So how would the body of this function will look like? The first condition, there would be a condition which would check for if the sum, if the integer that we are standing upon, can we include that integer in the generation of our final subset. That is, if the sum that we want to generate is greater than or equal to the integer that we want to include. If it is, then that's okay. We have two choices, either take it or do not take it. Otherwise, if the integer that we are standing upon is greater than the target sum, then there is only one choice, that is just skip that integer and move left, because an integer greater than the target sum cannot be used to generate the target. Okay, let me show you the body of this function. How will the function look like? Okay, so this is how the function will look like. Here we have the first condition. If the nth integer is greater than sum, we have only one choice. We just have to skip this integer because it cannot be used to generate this target sum. Otherwise, we always have two choices, either use this sum, either use this integer, or do not use this integer. If we are using this, then the target sum that we require would reduce by the integer which we are using. Okay, it is saying basically, okay, you want to generate sum from n integers, then include nth integer and try to generate this sum from n minus 1 integers. If it is possible to do so, then it is possible to do so as well. That's what this statement is saying. And the second case is, okay, we do not want to use this integer, nth integer, rather we're going to skip it because maybe the final set do not contain this integer. So that's what we are saying here. But even if by including or excluding nth integer we get true from one of these sides, either this returns me true or this returns me true, we have to return true because the positive answer must be propagated to the root of the tree such that there is at least one subset which gives me the target sum, and hence we OR these two results here. Fine. So this is the main recursive case, and the base cases are simple. If the sum becomes 0, that means we have generated our target set, then we return 0. That means if we exhaust the list, if we exhaust the array, then we return 0. Fine. That means we cannot generate any sum, we cannot generate this sum from the list which has no size, which is of size 0. So that's what it is saying. So let's see the time complexity of this code. Here you can see that initially the function is called for 4 integers and for this target sum, and at each level the function recursively calls at most 2 functions. Hence this is the branching factor, while the height of the tree goes up to the length of the list n. Okay, so that's why the time complexity would be 2 raised to the power n. So that is the time complexity. So n is the length of the array and n goes up to 100, and 2 raised to the power 100 is a huge number and it will not work within the time limits of 1 second. Hence we have to improve upon it. How we can improve upon a recursive solution? Well, if the recursive code satisfies the properties of dynamic programming, that is, there are overlapping subproblems and there is optimal substructure properties. I explained these properties in my another video, but for the sake of like this video, just see if the problems are repeating. Like here we can see that this problem is repeating. You can see that this problem is repeating here, then the problem is repeating, then we just have to, so these are the overlapping subproblems. The function is called here, it is called here again, and we are building the solution of a larger problem, a problem of larger size, from the solutions of smaller problems. Hence we satisfy both the properties of dynamic programming, so we can memoize the code that we have been given. Memoization basically is storing these results, the results of these function calls, such that whenever we require the results for that particular set of values, we do not have to call the function again to recompute the results. Rather, we simply return the results that we have stored for those function calls. Okay, so that's the idea of memoization. So let's see how we can memoize this recursive code in the next slide. Okay, so this is the recursive code. We are using a DP array of dimensions n cross sum. This is the dimension n, which is the number of elements in the array, while this dimension is basically the sum dimension, which gives me the sum along that array, like sum that we want to generate, target sum. And dpij, this is the dp matrix, and dpij represents, it's a boolean matrix or the matrix containing 0 and 1. 0 stands for a negative response, 1 stands for false. It says if it is possible to obtain a sum j with I integers. That's what this dp array is saying. Fine. So initially the dp array contains -1. Why? Because this is to check whether, for a particular set of values I and j. Here a value containing is like the computations are performed or not. If the results for that particular set of I and j are computed, then there would be some integer other than -1. Otherwise, there would be -1. So it is just to check whether the results are memoized or not. And these are the base cases which stays the same. This is the case of memoization. It is saying, okay, if the results are already there, then return those results. Otherwise, we check those two conditions that we discussed earlier. Check if the current integer is greater than sum. Then if it is, then simply there is only one choice. Call the function for the set which contains n-1 integers. That means move the pointer to the left by 1 and pass the same sum that we have here. That means we are not including the nth integer. Otherwise, we have two choices. Either we include that integer in the final subset, or we do not include it. Okay, and we store those results for the particular n and sum pair here. Fine. So what is the time complexity of this solution? You can see that we are using the function is called for unique I and j pairs or unique n and sum pairs. That means, okay, so only unique these pairs means these redundant calls are cancelled. All we have to do to count the number of function calls, we have to count the unique pairs. Unique pairs include the ordered pairs. So 1 2 is not equal to 2 1. Fine. So how many unique pairs will be there? If the number of integers goes from 1 to n and the sum goes from 1 to this sum, then the time complexity would be n into sum. Big of n into sum. So this is the time complexity. What is the space complexity? The space complexity is also n cross sum, because n is basically the n cross m is the dimensions of the matrix that we are using, or we say the dimensions of the auxiliary matrix that we are using here. Okay, hence the space complexity is also n cross sum. Fine. So that's how we have improved the time complexity from exponential to quadratic. And will this work for the constraints that we were given? We know that the length of the array goes up to 100 while the sum goes up to 10 raised to the power 5. So this will give me 10 raised to the power 7, and 10 raised to the power 7 divided by 10 raised to the power 8, which is the number of iterations done by computer in 1 second. It will give me 0.1 seconds, which is within the time limit of any online judge, that is 1 second. Hence this solution will work fine for the constraints that we are given. So after memoization, our code is ready to be executed and we can submit this code on the online platform. Okay, so this was memoization, but we know that in dynamic programming we have two approaches of solving a problem. Another approach to solve the problem is basically we know tabulation, or building the solution in bottom-up manner. Let's see how we can do that as well. In that solution, basically, why do we say it is a bottom-up approach? Because we know the solutions of smaller problems. All we have to do is to use those solutions and build the solutions of larger problems. So here what we do, we just have the same matrix. We declare the matrix here of n cross m, some dimensions. We initialize the first column, basically the column number 0, with true value, because it is always possible to generate a sum 0. That's why I'm initializing it true with any number of sets. That means we have a bunch of integers here and we want to generate a sum of 0. We can always do that, because just do not use any integer. That's all. and we putting false for the first row. Why we are putting false here? So this will contain false because simply we know, but we are saying that whatever sum you want to generate, I is non-zero here, you can say it starts from 1 to sum. Any non-zero sum I cannot be generated if I is greater than 0. Okay, it cannot be generated from 0 integers. It at least require one integer to be generated. Okay, that's what this statement is saying. So this is containing false, this is containing true, this is also containing true, and so on. So here we are using two pointers. The first pointer iterates over the rows, okay, pointer I, and the second iterates over the columns, pointer j. This is pointer j. Now what we are saying, okay, dpij, what dpij is saying here, or subset ij, we are using subset ij. We are saying, okay, j basically represents the sum. So we are saying, okay, if sum j is possible to generate or not. If j is less than the integer that we are standing, so we are standing at ith integer of the set. Here we are checking the condition corresponding to this condition. We have the condition here. So this is what we are checking there. Yeah. So checking if j is less than the integer that we are standing upon. If it is, then we cannot use this integer to generate j. Okay, so j is iterating over sum. We want the value for dp n sum. That means using n integers to get sum, to find our target sum. That's what we want. And j represents the sum, and it starts from 1 to sum. It goes from 1 to the target sum that we have here. And that's what we are asking. If this condition is satisfied, that means we cannot use the this ith number to generate j. In that case, we simply store the result which is present in the previous row for the same sum, because we are not including this integer here. But if it is greater than the integer, that means we can include this integer. Then we have two cases. Here we are using the previous case that we are not using, but here we are using it. Since we are using it, we have to know the result of the set which we had earlier stored where we didn't use this integer. Okay, so here what I am saying, okay, you want to use this integer in the set, exclude this integer and check if by excluding this integer, if it was possible to generate j minus set I minus I. If it was possible to generate this sum, then it would be possible to generate this sum as well. That's what I'm saying here. Okay, finally after the loop ends, I would return the subset n sum, because this will contain the final answer. Fine. So the space and time complexity stays the same. It is n cross m. This is the time complexity, or n cross sum, I would say, not m. And the space complexity is also n cross sum, because that's what are the dimensions of the matrix that I am using here. Okay, so thank you so much for your patience, and I have attached the code of these problems in the description, and let me show you the implementation of the solution. So this is the C++ implementation. This is the base cases. These are the base cases. This is the case of memoization. This is the case where there is only single choice of not using the nth integer, and this is the case where there are two choices where we can use the nth integer or we cannot use we cannot use the nth integer. Okay, and this is the implementation in Java language. Okay, and this is the implementation in Python language. So that's all for this video, and make sure to check out the code that I have attached in the description, and don't forget to like, share and subscribe, and give the feedback in the comments. Thank you so much.